welcome all to today's seminar. Okay, within the CSIM series. Okay, we are very happy to have Dr. Ahmed Alkhateeb, who kindly accepted our invitation to be our speaker today. Seminar title, Machine Learning Aided 6G. So, well, interesting topics we will see today. Leveraging sensory data for highly mobile and reliable communication systems. Dr. Khatib, he has the PhD from University of Texas at Austin in 2016. He spent some time at Facebook. Then he joined Arizona State University in 2018. Okay. He has received many awards, okay, and he is a highly cited researcher with more than 10,000 citations on Google Scholar. Impressive. So, with no more words, okay, Dr. Khatib is highly known in the community, and we thank you again for accepting the invitation. So please, the floor is yours. For the ones who joined now, okay, I would like to let you know that the seminar is recorded, okay, so that we can post it after the seminar, okay, on CSIM YouTube channel, okay, and it will be shared with the CSIM members. So, Dr. Khatib, thank you again, and the floor is yours.
All right, thanks a lot, Nizar, for the introduction, and thanks everyone for attending. You will enjoy this presentation. So in this talk, I will mainly present some of our work that we have been doing over the last 3-4 years on leveraging sensory data and machine learning to enable highly mobile and reliable communication systems, and in particular, MIMO communication systems. So this is joint work with my students, Goranj, Ahmed, Joao, Shrifen, Taufik, Mohammed, you, Nikhil, and Andrew, and all did great work over the last few years. So let's start with the motivation. So there are currently key trends in wireless communication systems, and some of these key trends are the use of large antenna arrays. So, for example, sub-6 GHz massive MIMO and mmWave terahertz MIMO, cell-free massive MIMO intelligence services. So all are ways of leveraging large antenna arrays. And another trend on migrating to higher frequency bands, sub-6 GHz to mmWave in 5G, to above 100 GHz in 6G and beyond. So these main trends are mainly driven by the demand for higher data rates. So they're the main motivation behind going to large antenna arrays and higher frequency bands is to access the spatial multiplexing gains, beamforming gains, and bandwidths available in these regimes to achieve higher data rates. But then with these trends also come other challenges. So for example, the use of large antenna arrays and narrow beams makes it hard for the base station and the infrastructure and the users to tune these beams, these narrow beams, to find the best, let's say, beam pair. So this beam training process is typically associated with high beam training overhead. Also at low frequency massive MIMO, acquiring that channel requires large training and feedback overhead. And this leads to difficulty in supporting highly mobile users. And also, since this beam training process is repeated very frequently, this poses challenge on the power consumption, especially at the user side. Also, the use of higher frequency bands, or the move to higher frequency bands, and the signal propagation at these higher frequency bands suffers from high penetration loss, high diffuse scattering, and this leads these communication systems to rely mainly on line of sight lengths and to be very sensitive to blockages. And this means that if the link, if the line of sight link is blocked by any pretty much any blockage, then this leads to sudden degradation in the SNR, and probably the link could be disconnected, and the user needs to reconnect to another base station. And this is associated, again, reduces the reliability and latency and increases the latency of the communication network. All right, so if we look at these two like sets of challenges. And broadly speaking, we can say that acquiring channel knowledge is a key to overcome these challenges. So, for example, if you assume for now that you have gene-aided basically channel knowledge, so you have channel knowledge that are available for free, then we can track mobile users. We don't need to repeat this beam training process, let's say, very frequently, which saves power consumption at the user side and increase battery life. And also, if we know channel in the future, then we can probably predict blockages before they happen and proactively move this and hand off these users to other base stations, enhancing reliability and reducing latency. So acquiring channel knowledge can say that it's the key to overcome these challenges. And if we can acquire this channel knowledge, the current and future channel knowledge for free or with very low overhead, then this could be very important in overcoming these challenges. So there have been, of course, a lot of research and directions over the last years trying to overcome these challenges and with large antenna arrays, reducing the channel acquisition overhead, with compressive sensing, with hierarchical code box, with multi-layer pre-coding and other approaches. But in general, they can maybe save one order of magnitude overhead, not much more than this. And as we increase scale the number of antennas, we need to come up with more interesting solutions and more efficient solutions. And also in terms of reliability and blockage avoidance, let's say, the main trends have been in research. We're mainly focusing on multi-connectivity, so kind of basically keeping the user connected to multiple base stations at the same time, so that if one link is blocked, can move to the other base station. But this reduces the utilization efficiency of the network resources. So how can machine learning help in this channel acquisition objective? So the general intuition is that why machine learning is interesting is that the channels are generally defined by the various elements of the environment, right? So the channel, intuitively or broadly speaking, we can write in a very high abstract way. We can write the channel vector, let's say. When I say channels, I mean channel vector, matrix, beamforming vector, channel covariance. So basically all these kind of channel quantities, we can write them as a function of the different elements in the environment geometry, materials of the buildings, scatters, etc., and the transmitter receiver locations, and so on. So the various elements of the environment, including the user locations and the communication terminal locations. But then the problem is that this function is hard to characterize analytically, and it changes from location to location, from site to site. So here comes the role of, or the kind of the motivation of machine learning in learning this hard to characterize function. So if you imagine you have a machine learning model and if we can model these inputs, the environment geometry, materials, locations, etc., and if we can train a machine learning model to learn how to map these inputs to the channel, how to basically learn this function. And the trick here would be if we can acquire these inputs basically with low training overhead or for free in terms of wireless communication resources, then this means that with low training overhead, we get these inputs, or we get some features that represent these inputs, and then a machine learning model can map them efficiently and quickly to the channel, so we can acquire this channel knowledge with low training overhead or for free in terms of wireless communication resources. So this is the general motivation. And now, interestingly, the two trends that I mentioned, as they pose more challenges, but at the same time, they also make the channel knowledge and the communication in general very dependent on user and environment characteristics. So for example, the user position, if we know the user position, can help in deciding the beamforming direction. If we know the building geometry, maybe we can identify a good reflector. If we know the object positions and shapes, that the dynamic object positions and shapes, so it can help maybe in inferring that a blockage is coming. And if we know the mobility pattern, maybe we can track the users. So basically, the this mapping from environment, geometry, materials, locations to channels become more, let's say, characterizable or not characterizable, more clear and more high correlation in as we go to large antenna systems and as we go to higher frequency bands. So this is interesting because this means that if we have some knowledge about the position, geometry, mobility pattern, etc., then this knowledge could be very useful in predicting, again, channel beams, blockages, etc. And this all leads to what we call as sensing-aided wireless communication. So how we imagine it is that we have an environment where infrastructure nodes and users both have sensors, and such as GPS, radar, LiDAR, camera, or even wireless sensors as antennas as sensors. And then using all these sensors, we acquire a lot of information about the users and about the scatters and the buildings, and etc. environments, such as position, orientation, shape, mobility pattern, electromagnetic characteristics, etc. And then with all this awareness about the environment and the users, this can lead to a lot of interesting applications, such as, let's say, line of sight beam prediction, non-line of sight beam prediction, blockage prediction, reflector identification, resource management, proactive blockage prediction, and handoff user clustering, scheduling, and so on. So we can enable a wide range of interesting applications that would save network resources and make utilization as efficient as possible with leverage of sensory data and with the leverage of machine learning. So this is the main motivation behind sensing-aided wireless communication. And now if we look at these sensors, we can maybe group them into two main groups. One is the antennas as sensors. We can look at the wireless communication antennas and receivers as sensors. So they sense the channel, they sense the electromagnetic propagation and the channel. And this channel implicitly captures some dependency on the environment, geometry, materials, and so on. So you can look at the channel and the wireless receivers, wireless communication receivers themselves as also sensors. And then how can we, maybe get the channel at some antennas and use this channel to predict or receive the signal at some antennas and use the signal to somehow predict channels and beamforming vector and covariance. And why this could be interesting if you are going to use channels to predict channels. So I will clarify this in the next slide. But generally, you can look at wireless receivers as wireless communication receivers as one type of sensors. And then the other type of sensors, you just group them as everything else, that non-communication, let's say, sensors. So position, camera, LiDAR, radar, they all could provide interesting features and awareness about, again, the environment, geometry, locations, etc. And then this knowledge could be mapped somehow to the channels, beams, blockages. So, all right. So in the next, on the rest actually of this talk, what I will do is that I will just spend a few slides on the first class of sensors, wireless communication receivers as sensors, and clarify why this could be interesting, especially with machine learning. And then the rest of the talk I will focus on the non-communication sensors. So wireless receivers as sensors, and here to really capture the significance and interesting gains of using wireless communication with machine learning to efficiently predict large channel matrices and beamforming directions with low training overhead. To do that, so we proposed this concept of channel mapping a few years ago, and the key idea of channel mapping is that if we have two groups of antennas, let's say two sets of antennas, M1 and M2, that could probably be at two different frequency bands or two different locations, of course, in the same environment, serving the same user. And this user could move within a certain environment and a set of locations. Then then for this setup, we will define a mapping function, GMF1, M1F1 that maps locations to the channels at the first set of antenna, and another mapping function that maps the positions to the channels at the second set of antenna. So this is just you know, the channel is a function of the position. So this mapping function always exists. Now we will also set one condition. So this is the only condition that the channel mapping depends on, which is assuming that the mapping from the positions to just the first set of antennas is bijective. So meaning that if we know the channels at the first set of antennas, we will be able to then the mapping from this channels to the position exists. Okay, and essentially this is the an underlying assumption in let's say fingerprinting and localization based on channel knowledge. So if we know the channel, then this can somehow lead us to the position. So imagine if you have, let's say, 8 antennas, and all what we want here to make this mapping bijective is to make sure that every 2 locations in the candidate set of locations would lead to 2 different complex channel vectors in this 4 or 8 antennas. Okay, so it's kind of one-to-one mapping. So the probability of having this one-to-one mapping, of course, increases as we have more antennas and increases as we have more scatters. So it's actually low frequency is probably better in channel bijectiveness and other factors. And the non-uniform, let's say, distribution of the antennas also help in increasing this channel, this mapping, bijectiveness of this mapping. So if we assume for now that this mapping is bijective, then this means that the inverse also exists. So if we can map the position to the channels at the first set of antennas, and if this mapping is bijective, then this means that we can map the channels at the first set of antennas to the position, and then since from the first mapping functions, we can also map the position to the second set of antennas. Then this means that the composite mapping also exists, which means that we can map the channels from the first set of antennas to the channels at the second set of antennas, or that this mapping exists. And now this is very interesting, because if this mapping exists, then using the universal approximation theory and neural networks, then we can there exists a complex enough neural networks that can learn this complex mapping from the channels at the first set of antennas to the channels at the second set of antennas, and under other kind of assumptions. So why this is interesting? Now, this means that if you remember that we didn't constrain the 2 antenna sets to be operating at the same frequency, or to have the same numbers, or to be in the same locations. And this means that if we have the channels at the first set of antennas, let's say at sub-6 GHz. So if the first set of antennas, for example, is operating at sub-6 GHz, while the second set is at another frequency, let's say mmWave, then if we know that channel at sub-6 GHz, and if this channel bijectiveness is satisfied, then we can map this channel knowledge again at sub-6 GHz to the mmWave channels or beams. So in that sense, we are using channels at sub-6 GHz that are easy to acquire. So it's not, channel knowledge is easy to acquire to get mmWave channels and beams that are hard to acquire. So we are getting channels again that are easy to acquire to and use them with machine learning to map them to channels that are hard to acquire. Okay, and this this has many other applications. So for in mmWave and massive MIMO. So for example, mapping in frequency. So I just give an example for mapping in frequency sub-6 to mmWave. Another mapping example in frequency is mapping uplink channel in massive MIMO to downlink channels in FDD massive MIMO. So you know in FDD massive MIMO, it's easy to acquire the uplink channels using just maybe a single pilot from the user. So acquire this simultaneously at all the antennas. But then it's hard to acquire the downlink channels because they require large training over the antennas and then feedback. So if we can map the uplink channels at the base station, so if the base station can acquire the uplink channel and then learns how to map these uplink channels directly to downlink channels, then it can save all this training and feedback overhead. So this is in one interesting application. Now, we have later on publications kind of discussing the practicality exactly and how to make this practical, and we can discuss this, but if you are interested, but I just highlighting this briefly and maybe refer you to the papers if you're interested in getting kind of going in more depth. And then we'll try to focus more on the non-communication sensors. And then other applications is predicting sub-6 GHz to millimeter wave, as I just discussed. So if you, again, using the channels at sub-6 GHz that are easy to acquire to predict maybe millimeter wave beams. And this is interesting because 5G and future communication systems will likely be operating anyway in dual band in sub-6 and in millimeter wave or higher frequency. So maybe the base station will anyway have this channel knowledge about sub-6 GHz and can use it for, let's say, free to acquire millimeter wave channels or beams. There are also other interesting applications for channel mapping if you look at the space. So in mapping in space, this means what? This means that we map the channels from some antennas to the channels at other antennas, kind of extrapolates the channel knowledge in space. And some applications, for example, in FDD massive MIMO, can maybe instead of downlink training all the antennas, can maybe downlink train some of them, and then use this channel knowledge to extrapolate and predict the rest of the channels. Kind of deep neural networks can learn how to map the channels from some antennas to the channels for the other antennas. So again, this reduces the training and feedback overhead, because now we don't need to train and feedback all the antennas. We only need to train and feedback subset of these antennas. Another application is actually similar application for this one also is reconfigurable intelligence services. So if we have hundreds or thousands of antenna elements, so do we really need to know the channels at all of them? Maybe we can acquire the channel at some of these elements and then use this channel knowledge to predict the channels at the rest of the elements, or the beams maybe directly for the rest of the elements. And we have a paper that kind of tries to explore this direction. Similarly, also for cell-free massive MIMO. So if you have a distributed antenna node, so maybe we also acquire the channel at a few of these or some of these antennas, and then feed this back to the processing unit that can leverage this channel knowledge to predict that channel at the rest of the antennas, distributed, and kind of saving frontal overhead and processing complex. So all these are interesting gains, again, of channel mapping, and really enable a lot of kind of interesting applications. So if you're interested, so this paper is available also on arXiv, and we talk more about different applications, and we have also journal papers that's coming soon. All right, so now let's move to the second category of sensors. Let's call them maybe non-communication sensors: position, camera, radar, LiDAR, IMU, and all these kind of sensors. Now, why are they, again, interesting? So I'm going to try to highlight this in the beginning. And now if we start with these sensors, so it makes sense to start with position. So, and this is, I think, the first modality or data modality, or the first sensor that people started looking at, is can we use basically position information to predict channels or beams or channel covariance matrices. And the advantages here are that it's easy, simple to acquire. It's easy to acquire position knowledge. Can use maybe simple machine learning and lookup tables to predict beams or channels. Maybe you can build some lookup tables also for position to beam mapping or channel mapping. But then the limitations that they mainly work outdoor. It's hard to acquire channel knowledge indoor. Also, the channels and beams are not really just a function of position. They're also a function of the environment geometry and scatter and so on. So there is some ambiguity as you just map location to channels. So you need to also condition this knowledge on this position knowledge, on the knowledge about the environment and geometry and all that. So the position data may not be very sufficient to accurately predict beams, especially in non-line of sight cases and channels. And we have more results on this. So with this motivation, 2019, 20, so we're asking, okay, why not we use maybe vision, camera information, okay, so that provide a lot of kind of interesting and rich information about the environment and the moving scatters, and maybe can help also identify the user locations and so on, to help the wireless communication functions, such as directing beams and predicting blockages. And again, the motivation here is that first, cameras are available in many user devices now and can be easily added to base stations or access points. Of course, there are some privacy concerns but regardless of, I mean, beyond this privacy concerns, I mean, maybe in outdoor locations or something, I mean, it could probably be less sensitive to privacy concerns. And we can leverage this rich visual information that these devices that are already there to help the communication system. So this is one motivation. The other motivation is that as we go to millimeter wave and then now to maybe above 100 gigahertz in 6G and beyond, the lengths communication lengths become more line of sight. So, and kind of close to visual line of sight. So which makes sense that the base station will kind of visually see the users and the blockages, etc. So it can probably use this knowledge again to help the communication system. So for example, instead of searching for the best beam blindly everywhere, I mean, if the base station can see that this is a user here, then it can probably narrow down the search space to these 4 or 5 beams. Or if it can identify where is the user and track maybe the bounding box of the user, then it can and see maybe a bus coming to block the length, and it can proactively predict this blockage. So that was the motivation, and to start exploring this topic and this research direction, so we need to have a data set. And for that, we in 2019-20, so we built this data set called it ViWi Vision Wireless Dataset, which essentially try to plot or try to generate data that is coexisting wireless and visual modality. So the same environment, it's a synthetic data set. So the same environment, we built 3D environment in, let's say, Blender, which is a game engine, to provide high quality, high fidelity visual data. And then we take the same exact model to Wireless Insight, which is an accurate 3D ray tracing simulator to generate wireless data. And then having these two data modalities together, now we can, for example, associate the two. So say if this is the infrastructure and if this is a user location and this is the geometry of the environment, if this is then in this scene, in this visual scene, that was the channel. Okay, so we can now have this sort of coexisting wireless and visual data. We have also other modalities that we added later on, such as position, LiDAR, and LiDAR data. And with this data set, so this is a sample of the data set. For example, here we know the channel, and we use this channel to generate the beam. And this is a visual scene, so you can see maybe the beam is kind of pointing towards possible reflectors when the car goes to non-line of sight. And with this actually data set, also we organized machine learning competitions. It's very interesting in 2019 or 20. We had more than 40 teams participating in this competition, kind of ViWi beam tracking. And some of these results that we explored as basically vision-aided, let's say, beam prediction. So can we use vision to predict beams? And again, a very simple data set that we started with. And this is simply, this is as a sample of the data set where you see a vehicle moving. And then we input this visual data to ResNet 18 neural network with modified last layer to predict the beamforming vector. And we show that we can predict this with 90-something accuracy for top 1, top 3 beam, best beams. And then we also explored the potential for blockage, use visual data for blockage prediction. So for example, and proactive handoff. So for example, here we have for example, this is a sample where we have a sequence of visual data. And then we use this sequence. So if the base station sees this sequence of visual data, and it knows what is the beam that it's using to track the user, then having this sequence of visual data and sequence of beams, the machine learning model can know a priori if a blockage, let's say a bus is coming to block the link. Okay, so it can maybe identify the bounding box of the bus, and then if it is getting closer to this beam direction, then it can predict that this is going to block the link and try to maybe proactively make some action. So for example, proactively switch to another beam or another base station. And we show that we can get maybe 10, 12, 15% improvement in this using just vision for blockage prediction. All right, so all that was based on, all these results were based on synthetic data. And then the important question that I'm sure some of you are also thinking about is, can we realize these gains in practice? Now, if we take this very simple, okay, if we have a very simple model with a car in front of the base station and synthetic data, maybe the model can memorize, maybe the model the setup is very simple. So if we can take this to real data with real impairments and real kind of deployment scenarios, will these gains also be there? I mean, can we realize these gains in practice? So with this motivation, so we moved to attempt to build a large-scale real-world dataset, what we call real-world multimodal sensing and communication dataset. We call it DeepSense. And essentially, it is the idea here of DeepSense dataset. That DeepSense dataset is to put together coexisting sensing and communication data modalities. So, for example, mmWave beamforming or beam training result, and then at the same time we'll have a camera, a picture taken from a camera, and LiDAR sweep and radar raw IQ data and GPS positions and so on. So we'll have all these kind of different sensing and communication data modalities. And then if we put them together, then this will enable, all these kind of interesting applications that I will discuss in a minute. So with this effort, we built different test beds ranging from mmWave to sub-6 GHz massive MIMO to reconfigurable intelligence surfaces. We also looked at different deployment scenarios from robots to vehicular, V2V and V2I, and drones. So with this kind of different sensing modalities, different hardware scenarios, we built this dataset, DeepSense 6G, which is I think the first, let's say, large-scale real-world multimodal sensing communication dataset that enables a wide range of sensing, communication, and positioning applications. And the structure of this dataset is we try to make it very simple. So it's essentially we have scenarios, and then every scenario, so the scenario represents a data collection session, let's say a large data collection session, and then every scenario has simply rows of data. Every row has these modalities. So it's kind of very simple structure. For one modality, you have time samples, and every time sample you have the coexisting data that came from communication and different sensors. So again, we have data about beam forming, beam training results. So this is, for example, this is a sample where you have beam power of 64 beams and mmWave phased array 60 GHz. This is a sample for image, that's RGB image that's taken from a camera. This is actually just a synthetic data, just to kind of represent LiDAR. I have some more kind of real data later on the slides. And this is the GPS position. And we have also radar and other modalities, IMU for some cases. And with this coexisting data sets, again, that represents different modality and different communication systems, sub-6 GHz, mmWave, and RS. In numbers, we have now more than data collected from more than 30 scenarios, representing again vehicles, humans, drones, robots, and elevated base stations and reconfigurable intelligence services, and more than 1 million in total multi-modal data points. So we have more than 1 million points. Every point has multi-modal data. And if you look at unique modalities, so it's kind of close to 5 million data points. So the data set is just available today, actually first day online, and deepsense6g.net. So you can access and maybe play with it if you'd like. And then the way we structure the data. So we offer the data in two ways. The first way is, as I described, just scenarios. So we have now 30 scenarios, and we are adding more in the next few weeks. Every scenario has just the full data set, so the full, let's say, long data collection session. And we summarize the scenario in a table. So there is a standard way in defining all the scenarios, so that if you got familiar with using one scenario, so you will be able to kind of later on kind of quickly kind of move to other scenarios as well. So because they all follow the same standardized way in the definition. And we use just a simple table where we have what is the DeepSense test bed that we use, the number of samples collected, and how many units were participating in this data collection. So every unit simply is that every session, there are a number of units, and every unit has multiple of sensors that are collecting data. So for example, a V2I session, a scenario, for example, we have a base station, or what we kind of call base station, with a number of sensors, a millimeter wave receiver, radar, LiDAR, position, etc., LiDAR position, and then we have also a vehicle collecting maybe position, camera data, LiDAR data, and so on. And then every one of these units are collecting certain data modalities that we just stack together in at the end. So again, I try to make this kind of a simple structure and standardized to make sure it will be easy to use. So this is a sample of the data set. So this is one of the scenarios, and we have also this kind of visualization for actually the full data set to make it also simple to debug. So you can use this video. So again, the video represents all the samples. So for example, scenario 9, we have don't know how many samples, and so close to like 6,000 samples, and they are all you can visualize them in this video. So we have a video for every scenario, and again, the video mainly I think could be useful for debugging. So for example, if we see that, let's say, in one particular data point, the beam power was very low, so you can go to this video and see that yeah, maybe there was a blockage, maybe a car was blocking the link in this particular sample maybe. All right, so this is the first way in offering the data as scenarios, and then the other way I will talk about it in the next slide. The slide and the next slide. So before I talk about this, just important to mention that with this multi-modal sensing and communication dataset, this enables a wide range of applications for communications, for example, beam prediction, tracking, blockage prediction, handoff, resource management, etc. And then also for sensing, positioning, ranging, imaging, detection, classification, object detection, classification. And again, since we have also this wide range of scenarios, so this also enables interesting machine learning studies on transfer learning, fusion learning, data fusion, and more. Now, the one main objective normally of having a data set is to have a common ground for benchmarking and comparing results. So for that, we also offer the data set in another format, which is task-specific development datasets. So we essentially, this is a screenshot I am taking from the website. So we have different tasks. So let's say beam prediction, current beam prediction, and the beam prediction you will find different modalities. So for example, vision-aided beam prediction, position-aided beam prediction, LiDAR, radar, and so on. And then for every, so for example, if we go to vision-aided beam prediction, so we offer a task-specific dataset for vision-aided beam prediction. So this task-specific dataset will have training, validation, and test sets. Every set has basically the input and output of the machine learning, the input and output of the model, of course, including the processing that you can do in the development. So for example, the image and the best beam, or the best top beams, and so on. So we have the input and output of the machine learning model. It kind of defines this machine learning task, so that everyone can basically innovate in developing an efficient machine learning model, and then we can all still compare the results and using the same exact data set to have some sort of ranking. And we have this kind of initial leaderboard ranking. And the hope here is that, kind of encourage the community to kind of develop more interesting solutions in these directions and be added to this ranking. So again, it's kind of a way to enable reproducibility of the results and benchmarking and for this wide range of interesting applications. So next, I will just quickly go over 2 example applications, beam prediction and blockage prediction that this dataset enables, and kind of give you some sense of what we can do with DeepSense. So the first example is sensing-aided beam prediction. So now, again, I mean, beam prediction is a challenging task in millimeter wave and above, and especially if we have large number of beams. So can we use the sensing data to reduce this beam training overhead? And now, can we do that using real-world data sets and show that these gains can be actually realized in reality? So this is a first task, and we studied this problem in different modalities, but there are still very, very wide rooms for improvements and for innovation and for extensions and so on. So we did some very initial results, actually, very initial studies in these problems. So for example, I mean, if we look at position, so we try to consider the position data and we adopted 9 scenarios out of DeepSense. And then we have codebooks, beam codebooks as part of the data sets of 64 beams. Now we can downsample them to have 32 beams, 16 and 8 beams. And then we designed 3 machine learning models based on lookup table, k-nearest neighbor, and neural network that tries to predict the best beam based on the position information. So if we now give the machine learning model a real world accurate, actually relatively accurate, also actually even more accurate than typical GPS. We are using GPS RTK in the dataset position data collection, which is somehow more accurate than just normal GPS. But anyway, so if we give the machine learning models this accurate GPS data, will it be able to predict the right beam and with what accuracy? So these are some initial results that we got. So again, this is across 9 different scenarios. So this is one of these scenarios, and here we look at the performance of the 3 different machine learning models, and we look at top 1, top 2, top 3 until top 5. And by top K, we mean basically what is the probability or the average accuracy that the best K beams predicted by the machine learning model match, or one of these beams match the ground truth optimal beam. We know the ground truth optimal beam because we have the full beam training results. So now we can actually measure the top 1, top K accuracy and so on. Of course, as we increase the number of K, so for example, top K, what the kind of the practical significance of it is that it means essentially that we can use machine learning model to, let's say, get the position and predict the beam, predict the top 5 beams. And then we take these top 5 beams and do fine tuning over the air. So now instead of beam training over, let's say, 64 beams, we can now beam train over only 5 beams with the user to refine and find the best beam over the air. So this kind of reduces the beam training overhead from 64 to 5, while still achieving some good accuracy. So what is the results here? So with top K accuracy, with top K beam training, with neural network, let's say we can show that we can get up to 90% accuracy, which is good. But then in the same time, with top 1, for example, we get only 40%. So which is somehow interesting. I mean, if you think about position to beam, it's kind of intuitively seems like a simple problem, but actually using real data, it is not as, let's say, high results or good results as we would typically get with synthetic data. And the reason here goes back mainly to the noise that we have in the data. So there's the GPS accuracy is still within some error, and also not just actually the GPS data quality, and also the beam forming data. So if you have 64 beams, then also there's some variation, there's some noise, and this noise in reality also kind of makes the data set itself a little bit noisy, and this noise impacts the performance of the machine learning. So this is kind of important insight that we'll not be able to get unless we use real data. And then this also, I mean, if you look at the results here, so we look at let's say the results of 9 scenarios. We look at the beam prediction accuracy, and we also look at how much power loss this best beam experiences compared to the ground truth beam. So interestingly, we see that even if we have 30, let's say 8% accuracy in predicting the top beam, this means actually less than 3 dB loss in the power, which kind of highlights the question is whether top K beam prediction accuracy is a metric that's kind of widely used in let's say evaluating results. Is it actually a good, is it the right metric to use, or should we just rely on power loss, which kind of captures the end objective of communication typically in data rate or SNR? But again, position may not be enough, because if we have non-line of sight scenarios, if we have kind of richer propagation scenario, and it's probably we need more information. We still present results for line of sight, but we expect that as we have more kind of complex scenarios, we'll need more, let's say, rich information coming from other sensor data. So we have also studied this same problem, sensing-aided beam prediction, but with radar. So now if we use radar data, and here we use a very simple radar that has 3 transmit antennas, 4 receive antennas, kind of low resolution radar relatively, and then kind of still use this low resolution, relatively low cost radar to help the beam prediction task in millimeter wave systems. So to do that, we now radar, one of the interesting aspects in radar is that we know already a lot of signal processing that we can do on the radar data. So we can, it's an area that has been there for some time. So now it makes sense that we first do some feature extraction on the radar data, do some pre-processing before we actually use just neural networks. So we tried several approaches here. I mean, if we do several pre-processing, let's say looking at range angle, range Doppler, or just use the raw data directly with the neural network, and how much accuracy we'll get with these different approaches. And also we compare this with a classical, let's say, we actually try to propose a classical solution that doesn't use machine learning, doesn't use neural networks, lookup table based mapping based. Let's say we get the range angle, and we try to detect the object, and then use some sort of lookup table to predict the beam. And with that, we looked at different things in terms of beam prediction accuracies. For example, beam prediction accuracy for top, again, 1 to K for the different approaches. So the first 2 represent lookup table kind of classical solution without neural networks, and then the rest represent different neural network with different processing models. So we're going to have radar cube. So here we input the radar cube as it is without kind of the raw data. Range velocity, range angle with 4 bends, and range angle with 64 FFT. And we look at different ones. So we can see that with, let's say, top 3, we can get maybe up to 80% with this machine learning model, while classical solutions represent 50-60%. And as we go to top 5, we can achieve more than 90% accuracy in predicting the right beam, and which is interesting. I mean, so radar is, again, a low cost, low resolution, easy to add to the network. And then with just radar and with relatively, very initial design of the pre-processing and then neural network, we can still achieve more than 90% in top 5, saving from 64 beams to 5, more than 90% of the overhead of the beam training. And again, remember that we saved all this overhead, more than 90%, with no overhead at all on the wireless resource. So we get this radar data for, let's say, free in terms of the wireless communication resources, and we use this radar data or position, whatever, to do this beam prediction task. It's kind of interesting gain that we get for almost for free in terms of wireless communication resources. And we also looked at other important aspects such as network inference duration and pre-processing and the number of parameters. So in conclusion, I mean, with machine learning, we can have processing plus inference less than time in less than 20 milliseconds. And this is an important point. I mean, if you talk about now the latency of these sensing modalities or the sensing data and how this latency, can you say that this latency is probably bottleneck for deploying the sensing aided wireless communication or not? So our vision here is that using almost any of these sensing modalities, we will have latency that is more actually than what we can get with just beam training. So if you do over the air beam training in 5G, let's say you can do that maybe in 5 milliseconds or something around that, or maybe 10 milliseconds. But then with the sensing modalities, we may actually need 20-30 milliseconds between data capture. So let's say capturing the image on the camera to the processing to the inference. So it's relatively longer than what you need in beam training. However, you can always think of that you can use this for future prediction. So you can maybe do this, collect a sequence of images or radar or LiDAR or position, whatever, and then use this sequence of data to predict the beams, maybe the next 10 beams. So now if you predict something in the future, you will be less sensitive to this latency in the capture and processing. So even if you need 100 milliseconds, it's still fine if you are predicting a beam that you will use after maybe 200 milliseconds, right? So this is kind of the general insight here on why this, why latency may not be a kind of a challenge for using these modalities, these sensing modalities. So next, we also looked at an important question, which is, can you now? Okay, this is good if you have maybe a certain object moving in the scene, but what if you have multiple objects? Will you still be able to do beam prediction for one user, even if there are other maybe to one vehicle, maybe even if there are other vehicles in the scene? So we looked at this problem again with different modalities, but for vision, for example, if you have let's say camera scene or camera data coming from the base station. Now, if you have other modality as well from the user, let's say either the beam-forming vector that the base station used to track the user, or the position of the user, or other modality of the user, then we can use this two together to do what we call transmitter identification. So we can identify the user or user identification. So we can identify the user in the scene out of the different, let's say, distracting objects by leveraging another modality that is kind of another attribute of the user. So for example, in this work, we look at the image and position. So we have now vision and position. So we have the visual data and also we have the position of the user. Now, combining them together, we can identify the user and distinguish it from the other candidate, let's say, communicating devices or objects in the scene. And this is demos that we did on using this. So we using vision and position, and we show how we were able to kind of, you see the beam is tracking the right user, even if there are other distractors in the scene, kind of maintaining high resulting power. We also applied similar beam training, vision aided beam training solutions to drones. So drone is also part of the data set. So we have a relatively large data set for drone communication that can also use in to design different interesting solutions for sensing aided drone communication. All right, so another example, last thing is sensing aided blockage prediction. So again, can we use the sensing data to predict blockages before they happen? And then if we can do that, then we can maybe do some, again, proactive action on resource management, on handoff, on beam switching, etc. So I'll present two approaches that we, two examples here on two different data modalities. The first one is wireless signature. So here, actually, we just rely on in-band millimeter wave receive signal to predict future blockages in millimeter wave. So the advantage here is that we don't need any kind of additional sensors. We just rely on the wireless data that's coming from the beam training, of the typical beam training that, let's say, the space station will do with the user. So it will receive some beam training power measurements over the different beams and over different time. So now if we look at this, let's say receive wireless power over different instances again in time, can we use this data to predict if a future blockage is coming? So here we did what we, so we proposed to use what we called wireless signature or pre-blockage wireless signature. So by pre-blockage wireless signature, we mean that before the blockage, let's say this is a blocking object, let's say a bus coming and kind of getting closer to the link, to the line of sight link. So as it gets closer to the line of sight link, then it basically works as a scatter in the environment with certain pattern in the wireless power. And what we kind of propose in this work is to use this wireless signature, this kind of pre-blockage wireless signature, the signature that is contributed by this blockage before it actually blocks the link, to predict that it is going to block the link. And again, the advantage is that we don't need any extra sensors. And what we were now to kind of test this idea, we built one of this, actually a few scenarios in the DeepSense with a setup where we have a transmitter location and receivers, transmitter and receiver deployed at the two sides of the street, so you can see them here. And then essentially what we did, just we kept recording the beam training power measurements to collect a large data set. We have more than 1,400 different blockages. So they are, they represent examples in buses and cars and bikes and so on. And in total, 120,000 data points. Actually, every data point is a sequence of power measurements. So it's something like this. We have like a sequence of beam power and time, and with manually labeled data for blockage or no blockage, and actually also what is the type of blockage. So we have 120,000 data points of this type, and then this kind of enables, kind of real-world study of these interesting applications. So we use this data set for, as I said, for wireless signature based or pre-blockage wireless signature based blockage prediction. So here, for example, as you see, this is one example where you see as the bus is getting closer to the link, line of sight links, you see some pattern. And this is essentially what we rely on machine learning model to learn. And in fact, what we were interested in here is to not just to learn if a blockage is going to block the link or not, but also to, to test if we can predict when exactly it will block the link, after how many instances it is going to block the link. And then also we're interested in seeing, like, can we from this signature identify if this blockage is, let's say, a car or a bus. And why this is important, because if it is, let's say, like a small object, maybe the link can just live with it. If it is a larger object that's going to block the link for, let's say, a few seconds, then maybe the link needs to kind of maybe do something and maybe switch to another beam or do something. So and then also the direction of predict also the direction of the blockage, as the direction is very important, again, for the same reason, to kind of predict where to give kind of more information to the network to know, like, what to do with this blockage. So these are some results that we got for this study. So the one on the left represents the top one blockage prediction accuracy versus the future interval. So if you have blockage coming in, let's say, 2 instances, and this is actually 0.1 second. So if a blockage is coming after 0.1 second, then we can predict this blockage with more than 80% accuracy. And if there is a blockage coming after, let's say, 0.5 seconds, so I mean, 0.1 seconds, like 100 milliseconds, which is, like sufficient time, I think, for communication systems. Like if a blockage is coming after 100 milliseconds, then 100 milliseconds is actually a very good time for the network to do some proactive action. And so on. And then, interestingly, I mean, we found that we can also identify if this blockage is a car or a bus, let's say, with relatively good accuracy, 70% or something. So, and this is out of 4 classes. Actually, we have also other classes in that we are kind of identifying from 3 or 4 classes in the paper. So if you're interested, we have more interesting results in this paper that's accepted in Open Journal Communication Society. Now, one observation here is that relying on wireless signature is interesting in predicting future blockage, but it's relatively predicting something that will happen in the next, again, 10 to 100 milliseconds with high accuracy. And then after this, the performance drops quickly. So can we do better? So what we, in terms of kind of predicting blockage well ahead in the future. So to do that, we looked also at vision. So in visual data, can give you maybe richer information or more rich information about the environment, which can help in doing that. And again, we have somehow realistic data set. We have different light conditions. So these are some data that were recorded in the night. Some data were recorded in the morning or noon. So can we still use, kind of this kind of practical data to have good performance in blockage prediction as one example. So we looked at this problem, and the idea here essentially is that again, the transmitter and receivers in this particular task and data set are stationary. So then the blockage prediction, it is essentially just predicting whether and when a blockage is going to block this particular stationary link. So it's more or less about identifying this object and kind of learning the geometrical relationship between this, let's say, bounding box and the link direction. So we designed this machine learning model. We have simply feature extraction, bounding box filtering, and then recurrent neural network for predicting the future blockage. And again, the same data set that we adopted in the previous study. And which is, by the way, also an interesting point that having also all these modalities together in the same scenario, let's say, this allows also comparing between different scenarios. So is position enough, or vision, like what is the gain in vision in addition to position, or LiDAR or radar, comparing to each other and so on. And also it also enables a fusion of these modalities. If you have different modalities, how can you fuse them, and when would, let's say, fusion make sense? All right, so back to this vision-aided blockage prediction. So here we plot the accuracy and F1 score of the blockage prediction of vision-aided block prediction, again, versus instances. Every instant represents 0.1 seconds. So, and as you see, with vision, and we can predict future blockage even 1 second before it happens with more than 80% accuracy, which kind of just shows how interesting using vision is for this task. Of course, if the user is mobile now, it will be more interesting and more kind of challenging, but can probably be all still extended. So with that, I conclude. So scalable MIMO is essential for 6G communication, sensing, and localization. But then it comes, and especially as we go to higher frequency, with challenges in mobility, power consumption, reliability, latency, and leveraging sensing and machine learning very promising. Is very promising towards overcoming these challenges for large-scale MIMO, especially at higher frequency. So learning the environment geometry, locations, materials, etc., and then using this knowledge with machine learning to learn the mapping to beams, channels, blockages, and then this enables proactive actions on resource management, user scheduling, and so on. A lot of kind of interesting applications. And then with DeepSense, the real-world large-scale data set that comprises multi-modal sensing and communication data can explore a lot of these applications, not just in sensing for comm, but also in integrated sensing and communication, and in just sensing, and have maybe vision and radar and LiDAR can do also a lot of kind of interesting sensing studies on this data and positioning. So for the future work, pretty much everything is future work here. So we have designing optimized machine learning model for all these interesting tasks wireless communication and sensing and positioning tasks, exploring more applications, and exploring machine learning, interesting machine learning questions on scalability, on how this, the learning could generalize, how the transfer learning could help, data fusion, few-shot learning, and much more. So again, if you are interested, so we have DeepSense website, which kind of puts the data set and also the applications and the task-specific description and data sets for these tasks. You can welcome to kind of try these codes and data and submit results. We can include this in the ranking table. Also, we have synthetic dataset THz MIMO, which is kind of enables channel mapping and studies on channel mapping and different wireless communication machine learning studies. And then on the group website, you can have also more kind of information about our recent research. Okay, with that, let's stop here. Thank you. And if you have any questions.
So thank you very much. Really interesting seminar, insightful. Okay, just for curiosity, so this data set is available very recent, right?
Today is the first day. Yes.
Today is the first day. Okay, good. So we okay, good. So we will publicize it more. Okay, so questions from audience. You can unmute directly and talk, or you can write it on the chat. Both options are fine. Well, meanwhile, until if you have questions, I have one question actually. Well, several questions, but one in, related to delay. So whenever you talked about the delay in the results, I was a bit confused. So especially whenever I would like to compare the delay, okay, that you report to the coherence time of the channel. Do you expect that the channel will change faster than this delay, and then we are talking about outdated results, or based on the results that you obtained, then this delay is kind of acceptable?
Yes, this is of course a very important question. So essentially, what we're kind of thinking is that this latency that again between capture time, processing time, and inference latency of most of these sensing-aided wireless communication tasks, they will likely be more than the coherence time. So in that sense, it might be hard to use this the result of this. Basically, the sensing results would be somehow outdated, and their applicability and usefulness for predicting something that would happen within a coherence time would be, of course, low. But then what's interesting about the sensing-aided wireless communication task is that you can maybe use this to predict something in the future, right? So you can maybe use sensing data that you collect, maybe a sequence of data, let's say 8, 10, let's say images or position or LiDAR, right, whatever data, to predict something that collected maybe over 10 coherence times, to predict the best beam or the best 5 beams that will happen in the next maybe 3, 4, 5 coherence times, right? Mm-hmm. So if the user is moving, you can maybe like get some sensor data about this user device, over maybe a few seconds, and then use this, or a few tens of milliseconds, and then use this information to predict what will be the best beams to serve this user in the next 3, 4, 5 coherence times, right? Mm-hmm. So this is a way to kind of overcome this latency overhead that's typically associated with most of these sensing devices.
Very good. So in short, so to take it for now, okay, it is somehow outdated, but it is useful for making predictions for future events, future coherence time. Perfect.
Exactly.
Perfect.
So that's why I see this as more kind of for proactive predictions on channels, on beams, on blockages and resources and so on.
Okay, so thank you. Okay, I have a question here by Dr. Amr Al-Wakil. Okay, he asked about whether you have data under different weather conditions. I think that most of the data that you have is for line of sight, outdoor one. From the videos we saw, it is good weather, let's say. Even I saw some of them that they were night, okay, and then you used some pre-processing techniques in order to extract more features whenever they are at night, so that you improve the images, right? So his question is, for other weather conditions, have the data been included in the data set or not yet?
Yeah, this is a good question. So we just kind of before answering this weather condition, we have data actually for outdoor and indoor. So we have some scenarios. So again, we have almost 30 scenarios now. We are adding more scenarios in the next few weeks and months. But for the 30 scenarios, they include cases for indoor as well as outdoor. Yes, the results I presented are more outdoor, but we have some scenarios also for indoor. They represent also different. I mean, for outdoor, as you highlighted, Nizar, so we have different times of the day, so day and night and so on. We have very little, I think, weather conditions training. I mean, just by chance, one time it was raining. So we have some, I think one of the scenarios we have raining, but yeah, I mean, rather than or kind of relatively clear weather. We plan to add more as we go. So this kind of the data set is structured in a way that would just hopefully enables the growing, and this is what the motivation behind is, having the standard definition so that we can keep just adding more scenarios in the future. So we plan to add more actually in different weather conditions, but currently, yeah, I mean, all are clear weather.
Okay.
We have also actually different, so with different times of the day and with different days of the year in Arizona, we have also different, like, let's say, temperatures and things like that, but a little bit affecting the hardware maybe, but not really kind of big changes in the weather.
Yeah. Well, the reason is Amr Wakil is based in Kingston, in Canada, so he expects that you will do measurement with the snow, I guess.
No, snow maybe. Okay, yeah. We need to move from Arizona to that. That's right.
Yeah. So I have another question here by Abdurrahman Ramadan. Okay, he is thanking you for the interesting talk, and he is asking what kind of CNN models and RNN models, okay, you have used, and if they have been reported in the papers, I guess, right?
Yeah, of course. Yeah. So yeah, I kind of didn't go in detail in any of this work, but yeah, I mean, every paper, every work is discussed in the paper, and the paper we discuss in details the specific machine learning model. For RNN, mostly gated recurrent neural networks. CNN are different approaches for different models for different use cases. So yeah, maybe you can check the papers maybe for more details, and let me know, of course, if you have any questions.
Yeah, for sure. One question by Mr. Ibrahim is he is asking what is the radar that you used. I remember you said it is a low complexity and not very expensive one.
Yeah, it is a TI module single chip radar that we have here in this particular scenario. FMCW radar, 4 gigahertz bandwidth, 3 transmit antennas, 4 receive, fully digital receive antennas. So it's in 76 to 81 gigahertz. Yeah.
Okay, perfect. Okay, so yeah, Amr, okay, good. More thanking, okay, for the nice presentation and talk. One last question from my side. Whenever you said about the real data, okay, you said that they were kind of different because of the noise. Have you identified what is the source of the noise? Is it interference from other transmitters, or it is just background, let's say, thermal noise?
Yeah, so
because I saw that it has decreased a lot the performance.
Exactly, and this is this was actually was very interesting because when you I guess you're asking about position aided beam prediction. So we're expecting to get maybe 90% accuracy because the position to beam seems like a like a very direct mapping and clear mapping, even with lookup table maybe. But yeah, so different sources of noise. So for the position, so we have input noise and label noise. So the input noise, input here is position. So we have just the GPS noise error and error. We have the in the output, the labels we have also beam the beam noise. So the beam noise actually, or let's say the inaccuracy in beams, comes mainly from two sources. First one is just the noise, that is the white noise, or the receiver noise, and also comes from the fact that we have here oversampled codebook. So meaning that even though we have 16 antennas, the phased array, we used 64 beams. So as you have 64 beams, so I have another figure, but it's not here on the beam patterns. We measured the beam patterns. So there's in some cases you have some sort of overlap between the beam patterns. So unless you are, so basically if the position moved maybe 10 centimeter or 20 centimeter, it will likely go to another beam. So this kind of very little sensitivity or very high sensitivity actually to little changes in the position, because we use oversampled beam codebook. So that was also important. So that's why we tried to look at the results actually with different sizes of codebooks. So as you see with 64, we have lower than 32 than 16. So 16 is what we call, let's say, close to DFT codebook, or just using close to orthogonal beams. So meaning that, it's kind of with low probability, the same position would, or with little change in the position, it will go to another beam. So here we have, somehow better results in top one beam prediction accuracy, but still, I mean, lower than, let's say, what you expect in synthetic data. And again, the position noise, and then the beam measurement noise, the receiver noise, and the high overlapping between the beams. So now, in terms of practicality, some of these, like some applications, actually, let's say in 5G, there are different types of codebooks. So there's SSB codebooks, which are normally used in the initial access. So these codebooks normally use, let's say, a few number of relatively wide beams and without much oversampling. So I mean, maybe you can, in that case, you can expect something in this order of accuracy. But then if you go to, let's say, CSIRS beams or beams used for kind of refining and really data transmission, then they're more oversampled and narrower, and after some refining and beam training. So in that case, that would probably be the accuracy if you go on for these.
So you expect that because a lot of research has been done on codebooks, how to, whenever they are non-orthogonal, how to find the best codebook that is the most orthogonal possible. Okay, so do you think that that will improve the performance?
Yes, yeah. I mean, this could be also interesting.
Interesting topic for research. Okay, good. So with no more questions from audience, okay, we come to conclude the presentation. We would like to thank you again for the very interesting topics and so many discussed technologies, I would say, okay, that they are really interesting. Interested attendees can check papers, okay, and the preprints, I guess they are all available on archive, right?
Preprints are not yet available, but if you're interested, let me know. We can.
Yes, they can contact you. Okay. or the people who will listen to this later on YouTube also they can contact you based on that. So, Dr. Ahmed, thank you again very much for accepting the invitation for this interesting talk and for answering the questions, and for all the attendees for being here, and see you in future CSIM seminars. Thank you all.
Thanks, Nizar. Thank you very much. Okay, and thanks everyone for attending.
Thank you. Okay, bye-bye.